Today we'll be using matrices to solve linear systems of equations. Now, in the past we have used methods such as graphing, substitution, and elimination to solve linear equations, usually in two variables. But in this lesson we'll be needing to solve linear equations in three variables, so therefore we're going to need to use matrices instead of the other methods. So here's an example of a two-variable linear system of equations. We have 3x minus 4y equals 2, x plus 2y equals negative 4. Notice there's two equations, two letters x and y. In this case, the method to solve, we could use graphing. We could use a method called substitution, or we could use a method called elimination. The solution is an ordered pair. In this case, the solution to this problem is negative 2 comma negative 1, or an ordered pair, meaning there's an x variable and a y variable, so the answer has to have an x coordinate and a y coordinate. Now, a three-variable system of equations, we have x plus 2y minus 5z equals negative 9, 4x minus 7y plus z equals 30, negative 3x plus 4y minus 6z equals negative 24. Notice we have three equations this time. We have three letters that we don't know, and so the solution is going to be an ordered triple because we have three variables, and in this particular case we have the solution 2 comma negative 3 comma 1. Notice this is an x comma a y comma a z. We call this an ordered triple. Kind of like an ordered pair, but an ordered triple because there's three variables that we don't know. The method to solve this is not going to be graphing, substitution, or elimination because it's a little bit too difficult. So what we're going to do is we're going to use matrices to keep our variables in order. Okay? But just to remind you what the system of two variables will look like. If we have a system of two variables, we could graph the two graphs, and I gave you an example here. The solution would be the ordered pair where the two graphs intersect. That solution, which in this case is 3 comma negative 1, is the pair, this is the ordered pair x comma y, that satisfies both the blue line and the red line at the same time. This is the same equation, just written slightly different. For substitution, I would take my variable y and plug it into the other equation. So we have 4x minus y equals 13. But instead of y, I can plug in what y is equal to, which in this case is negative 3x plus 8. So we have 4x, negative times a negative is a positive 3x, and negative times a positive is a negative 8. So I have 7x minus 8 equals 13. Do a little bit of solving, and I find that x is equal to 3. So the ordered pair is 3 comma some other value. How do I find that other value? Well, I plug in my x solved point. So I have y equals negative 3x from the original problem, and I can plug in 3 there. So negative 9 plus 8 is negative 1. Notice it's the same solution, but I found it by taking one equation and substituting it into the other equation. The last method, notice again it's the same equation, would be to combine the two equations together. This is a fairly simple example because my positive y and my negative y are already opposites, so all I have to do is add the two equations together. So I have 7x equals 21. And I solve for my first variable, x is 3. I still have to solve for my second variable. I plug it into either the first or the second equation, doesn't matter to me. So I have 3x, but instead of x, I'm going to plug in 3. So 9 plus y equals 8. Solve for y, and I'm getting negative 1. So these are three methods: graphing, if you took time to graph it, which I graphed it for you. Substitution, you take one equation and plug it into the other equation. And then elimination, where you add the two equations together. The elimination example I gave you was super easy. There was a much harder examples of elimination when the two variables aren't equal but opposites. So you have to do a little bit more work there. But that's how you would solve a two-variable system of equations, one of the three methods. Now, when solving a variable of three equations in three variables, this process for solving using graphing, substitution, or elimination gets ridiculously hard. It gets so much more difficult. So using graphing, substitution, and elimination for three variables is just too difficult. Instead, what we're going to do is we're going to use matrices to keep the variables in order. So we need to go through some definitions of what a matrix is. So a matrix is a rectangular array of numbers arranged in rows and columns, placed inside brackets. So an example would be 4, 2, 3, 8, 1, -3, 1, 4, 2, 1, 1, 0. This is a row, 3 rows. We have 4 columns. We have numbers. Notice there's no commas. We just have numbers arranged in vertical and horizontal columns and rows. Notice that you have to keep things lined up a little bit nicely here so that you know which one is in which column. Okay, so just be a little bit clean and neat there. The definition of matrices is just plural of the word matrix. Okay, just a heads up there. And then elements, the elements are just the numbers or values inside the bracket. So 4 is an element, 3 is an element, all of the numbers inside the matrix is an element. Okay, the matrix that I gave you here as an example is a 3-row by 4-column matrix. We call that a 3 by 4 matrix. Another example could be -1, 3, 7. This would be a 3-row by 1-column matrix. Or we could have a square matrix here, 2 rows by 2 columns, 2 by 2. Okay, so here's some examples of matrices. We are going to use these matrices to find solutions to systems of linear equations in higher numbers of variables. The next definition we need to talk about is an augmented matrix. An augmented matrix is a matrix with a vertical bar separating the two columns into two groups. Usually we use an augmented matrix to rewrite a linear system of linear equations. So we have a system of linear equations, and what I want to do is put it into an augmented matrix. I want to just take the values or coefficients of each of the variables. So the coefficient of the first variable, x, is 3. So I'm going to put all the x's in the first column, all the y's in the second column, all the z's in the third column, and then all the numbers in the last column. I want to separate the x, y's, and z's from the numbers because there's an equal sign there. So for the equal sign, that's where I'm going to put my bar. That's what makes it an augmented matrix. So my first variable is x, which has a coefficient of 3. My second variable, y, has a coefficient of +1. My z coefficient is a -1. Equals, that's where the bar comes in, and my number is 9. On the next one, the coefficient of x is -1, the coefficient of y is -1, the coefficient of z is 3, and the number is 3 on the other side. Then we have 1, 2, -1, and 0. Notice I have all of the information, the x, the y, the z, the equals, and the number, all just a little bit more condensed without all the variables. And if I keep everything organized in my columns, then I will always know what is x, y, and z without having to do as much writing. This is really going to help us when we're trying to solve later. On our next problem, notice I have some missing variables here. On the first equation, my x is a coefficient of 1, my y has a coefficient of -3, my z has a coefficient of 2, and my number on the other side of the bar is 12. For the x coefficient in the second equation, there is none, so I have to put something there. I'm going to put a 0. The coefficient of y is 1, the coefficient of z is 4, equals -3. On the last equation, all I have is a z, so the coefficient of z is 1, so I can go ahead and put that in the z column. and the x and the y have zeros. And that would be my augmented matrix. On the last one, notice it's a little bit crazy here. I have still x, y, and z variables. Not every equation has all three, but they are all present, at least in all three equations. So the first one, I have 3x, so I put a 3 in the x, minus 5z, so I put a negative 5 on the z. That means a 0 for the y, equals negative 12. On the second equation, there isn't an x, so I put a 0 there. 4 for the y, negative 1 for the z, and then 5 for the number. And then 2, negative 3, 0, negative 4 for the last one. Anytime you don't have a variable, you plug in a 0, making sure that you keep those columns nice and neat. Our next definition is called echelon form. A matrix is said to be in row echelon form if there are ones down the main diagonal. That's from the upper left-hand corner down to the lower right. And then there also has to be zeros below that one. Okay, what does that mean? Let's take a look here. We have a 1 down the diagonal, and below those have zeros. That means it's in echelon form. Why is echelon form so helpful? Well, down here at the bottom it says, so if the matrix is in row echelon form, then what we could do is use back substitution to solve for the system. Let's take a look at the next example here. Notice that I have ones down the diagonal, and I have zeros below it, which means this example is truly in what we call row echelon form. Okay, why does that help us? Well, we talked about back substitution. What the heck is that? What we're going to do here is just like when we put the system of equations into an augmented matrix, we're going to do the opposite now. What I want to do is take this matrix and rewrite this augmented matrix back into a regular set of equations. So I can rewrite that as x plus 2y minus z equals 0. The next equation has no x's, so I'm just going to start with the y. Y plus 2z equals 3. And then the last equation has no x's, it has no y's, but it has a z. Z equals 2. Once I have it in row echelon form, the matrix, I can use back substitution to solve. Just like I use substitution with a two-variable system of inequalities, because it's in row echelon form, this is possible to solve using substitution. I know that z is equal to 2. So what I can do is I can rewrite these equations because it's in row echelon forms with the ones down the diagonal. Notice that there's a 1 here for x, a 1 here from y, and a 1 here from z. I'm going to solve each of these equations for the x, the y, and the z because it's going to be fairly simple. So right now what I want to do is I want to take the 2y and the minus z and put it to the other side. What I'm going to do, instead of using a lot of algebra here, I'm just going to use something called transposition. If I want to pick up the 2y and move it to the other side of the equation, all I have to do is change its sign. I picked up the positive 2y and I put it to the other side. I picked up the negative z and I want to move it to the other side, and that makes it positive. And then the 0 didn't move sides at all, so he stays the same sign. In this case, 0 doesn't matter all that much, but notice that the 2y and the z changed signs, but the 0 did not. Let's do this again for y. The 2z needs to move over so that the y can be all by itself. We're trying to solve these for the ones down the diagonal. So I want y by itself, so I need to move the tz. So that puts it to the other side and makes it negative 2z. What happens to the 3? Well, the 3 stays the same sign because it didn't move. It was already on the right hand side, it stays on the right hand side. And the last one, well, z is already by itself, that one was obvious. So I know z is equal to 2, I can go ahead and put that in my equation. Now I'm going to use y is equal to negative 2z plus 3, but I know what z is. I know z is 2. So I can go ahead and evaluate that, and that gets me negative 4 plus 3, or negative 1. So I know that z is negative 1. So I started with the z, I substituted back up into y, which is why we call this back substitution. Now I'm going to take the z and the y and back it up and substitute it into the equation for x. So x is equal to negative 2 times y plus z plus 0. But the y I know is negative 1. The z I know is 2. So I'm going to go ahead and plug in those values, and I get 2 plus 0, which is 4. So therefore x is equal to 4. So row echelon form is really important. If I'm in row echelon form, then I can back substitute and get the solution to the system of equations.